Okay, so today we're going to look back at Lewis structures and get more in depth with them. So first I want you to think about which one of these Lewis structures for CO2 is correct. So pause right now and think about this. I will give you a hint. Two of them are correct. The other two are incorrect. So, what happens when there are multiple possible Lewis structures? So those first two are potential Lewis structures for CO2. When you have these multiple different Lewis structures, you need to calculate the formal charge for each atom in the molecule. So for CO2, you would do the formal charge of the leftmost oxygen, the carbon, and then the rightmost oxygen. So what is formal charge? It is the charge the atom would have if each bonding electron pair in the molecule were shared equally between its two atoms. So the charge it would have if the bonding electron pair shared equally between both atoms. So how do you calculate it? First thing, you need to know all unshared or non-bonding electrons. They are assigned to the atom on which they are found. For any bond, single, double, or triple, half of the bonding electrons are assigned to each atom in the bond. So a single bond has 2 electrons. So one of those electrons goes to one of the atoms, the other electron goes to the other. So the equation is formal charge equals the number of valence electrons of that atom minus 1/2 of the bonding electrons minus the non-bonding electrons. So I want you to calculate the formal charge of atoms in the cyanide ion. So cyanide has the formula CN minus, and the Lewis structure looks like this. So, with that information, calculate the formal charge of atoms in the cyanide ion. So, we're going to start with carbon. How many valence electrons does carbon have? I look at my periodic table, I find which group carbon is. 1, 2, 3, 4. It has 4 valence electrons. How many bonding electrons does it have? I come up here to my Lewis structure and I have 1, 2, 3 bonds, which is 2 electrons each. So that gives me 6 bonding electrons. And how many non-bonding do I have? Back to carbon, I have 2 dots, so I have 2 non-bonding electrons. So now I use my equation, do my valence electrons minus 1/2 of my bonding electrons minus 2. So that gives me my formal charge of carbon, which is -1. I then do the same thing for nitrogen. So I have 5 valence electrons, 6 bonding, 2 non-bonding. So that becomes 5 minus 3 minus 2, which equals 0. And the way I put those charges, identify those charges, formal charges for each atom, is I write them above the atoms in my Lewis structure. So that's how you calculate the formal charges on the atoms. Come back here. Oh man, hang on. Okay. So now let me erase all of this. Okay. So now let's look back at CO2, and I want you to calculate the formal charge of each atom for both of the Lewis structures. So remember, our Lewis structures were the double bonds, or 1 single bond and 2 triple bonds. So now pause this video and calculate the formal charge on each atom for both of the Lewis structures for CO2. So your work should look similar to mine. So this first row here, this is my leftmost oxygen, my carbon, my rightmost oxygen. So these all have a formal charge of 0. When I move to this right one, this oxygen has a -1 charge, my carbon still has a 0 charge, and my other oxygen has a formal charge of +1. So with that information, which one do you think is more correct? So deciding which Lewis structure is more dominant is basically saying which one is the most correct Lewis structure. So when you have multiple, you do the formal charge analysis, and the dominant structure is going to be generally the one in which atoms bear formal charges closest to 0. So for that CO2, that Lewis structure that had the double bonds, all of those formal charges were 0. So that one's going to be the dominant structure. The second way you can do the dominant Lewis structure is the one where any negative charges reside on the most electronegative atoms. So if you don't have a 0 formal charge on all your atoms, then look and make sure that the one that has the negative formal charge on your most electronegative atoms, and that's going to be the dominant structure. Important note here, formal charges are not the real charges on the atoms. They simply are a bookkeeping convention so that you know which Lewis structure is dominant and which one tells you the shape of the molecule. Okay. So for ozone, or O3, what happens if neither structure is dominant? So ozone here, the placement of the atoms is the same, but the placement of the electrons is different. So that double bond is in a different spot, but the atoms are in the same location. So neither one of these is dominant, and it's called resonance structure. So if neither are dominant, or if you have multiple and none of them are dominant, they are called resonance structures. So the way you draw the resonance structure is you keep both Lewis structures and you draw this double-sided arrow between the two to identify that the structure is basically the average of the two. So these, you have two equivalent dominant Lewis structures that both contribute equally to the actual structure of the molecule. So the example I give is when you're creating green paint, you mix blue paint and yellow paint. And so that green paint is the average between that blue and yellow mixture. It doesn't jump to be blue sometimes and yellow sometimes. It's that average between the two. Similar here with ozone, it doesn't jump between the structure on the left and the structure on the right. It's always the average of the two structures. So resonance is especially important in organic molecules such as benzene here. If you notice, there's 3 double bonds and 3 single bonds in that carbon hexagon. And so benzene is that blend between those two resonance structures. And this is how it's typically drawn without the hydrogen bonds. It's mostly just those that's carbon hexagon. It essentially emphasizes that the carbon double bonds, they're not assigned to specific edges. So these show those double bonds, but then this circle here, it just tells me that half of those 6 bonds are double and half are single. And I don't know where they are. And for benzene and most hydrocarbons, it actually doesn't matter because experimental data has shown that the length of the single bond and double bond in these molecules have the same length. So now with Lewis structures, we've seen a few examples to exceptions to the octet rule. So we're going to go through the 3 exceptions. The first one is molecules and polyatomic ions that contain an odd number of electrons. Odd number of electrons. So this occurs in a few molecules, polyatomic ions. It's essentially the complete pairing of the electrons is impossible because you have an odd number. So an octet around each atom simply cannot be achieved. Just can't. So let's look at NO. How many valence electrons does NO have? We have 5 for nitrogen, 6 for oxygen, gives me a total of 11. So the Lewis structure here would look like this. Or so in each of these, one of the atoms does not satisfy that octet rule because I simply don't have enough electrons to do it. So you can calculate the formal charge for both of these and see if one is dominant or if they're resonance structures. I did not do that, but you are free to. Okay. So the second exception, molecules and polyatomic ions in which an atom has fewer than an octet of valence electrons. So we've talked about a couple of them that have fewer than an octet. thinking hydrogen and helium. So we have fewer than 8 valence electrons around an atom in a molecular polyatomic ion. They're relatively rare, except for that hydrogen and helium. Most often they occur when the compounds have boron and beryllium. So if you see a compound with boron and beryllium, think about this exception. This may apply. So BF4, the dominant Lewis structure, looks like this. Okay, so that boron in the middle does not satisfy that octet. You could have this and get 3 resonance structures where that double bond moves around. So, but this one that has the boron only has 6 electrons around it, that's the dominant structure because the 3 resonance structure with 1 double bond, it forces that fluorine atom to share additional electrons, which is inconsistent with fluorine's electronegativity. You can analyze the formal charges of these, and it'll tell you that the 3 resonance structures that has the 1 double bond, that these are unfavorable, and this one's the dominant structure, even though that boron doesn't satisfy that octet. Okay, last exception. Molecules and polyatomic ions in which an atom has more than an octet of valence electrons. We've seen this with phosphorus and sulfur, but now we'll look at which other atoms this could work for. So, molecules, polyatomics, in which there are more than 8 electrons in the valence shell of an atom. So PF5 would have that central phosphorus and 5 fluorines around it, like this. And then all my dots. So how many valence electrons does that phosphorus have around it? It has 10. The 5 bonds, which give me 10 electrons. So, molecules and ions with more than an octet of electrons around the central atom are called hypervalent. Other examples of hypervalent molecules and ions are listed here. SF4, ASF6, -1 ion, ICl4, -1 ion. So, hypervalent molecules occur only from central atoms from period 3 and below. They form in these periods because of the relative large size of that central atom. So those atoms are large enough that they can attract more than that octet of electrons. So they occur most often when that central atom is bonded to the smallest, most electronegative atoms. So like fluorine, chlorine, oxygen. So when you see essential atom from period 3 and below bonded with fluorine, chlorine, or oxygen, you may need to think of the hypervalency molecule. Those are all the exceptions to the octet rule. So looking at SO3, there are 7 Lewis structures for SO3. So with those 7 structures, 3 of them have a single double bond. I will draw one of each, and then I think you know that the double bond can just move to make equivalent diagrams. So I could have 3 of these. Could also have one where I have the 2 double bonds. Or I could have one where I have all double bonds. So for this, which structure is more dominant? Do you look at the one that satisfies the octet rule? Or is it the one that obtains the favorable formal charges? It's actually a trick question because chemists are currently debating this idea. They're not quite sure which one would be the dominant structure. They don't know which has a greater influence on the structure, the octet or the charges, formal charges. So just an interesting idea to throw out there.